Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We continue with our introductory module. Today is lecture 4, we continue our discussion on statistical framework. So remember what we discussed, statistics is all about basically making decision about potential outcomes of all possible measurements based on some observed measurement. What does that really mean? Well, you have we have an experiment which can potentially end up in different results. For example, if you roll a die, it can end up in 6 possible values. Now, potential all possible measurement means with that particular die, whatever the rollings happen in past, the results of that, currently when you are rolling, what is happening, and potentially all the rollings that are possible in future. So, outcomes of all possible experiments that are done, that are being pursued and that are potentially going to be done in future. The outcomes of all possible experiments, the result of outcomes of all possible experiment is called your totality of all measurements, that is called population. You want to conclude about that, you want to study that, you want to understand that whole totality based on outcomes of some observed measurements. So, in this case you roll the die 10 times, you just record the results. Let us say you got 5 ones and 5 ones, 1 2, 1 3, 1 4, 1 5 and 1 6. So, if you have this observation, you want to predict, you want to say something about potential outcomes of all any possible rolling of that die based on this observation. Now, based on this observation, you can obviously say that like it is more likely to get 1. At the very least, you can say that maybe the die is more heavy towards 1 or something like that. So, this kind of thing, that is trying to predict outcome, all possible outcome of something, that is which outcome is how much likely, which outcome will be how much frequent, what is the relation between, let us say, chance of one outcome versus another outcome. You want to predict such things based on some observations you have done. That is broadly what statistics does. Now, you need to study it in a mathematically rigorous way, you need a framework, you need a mathematical framework that is provided by this thing called random variable. Now, the problem with classical, I mean some of you may have can recall probability that people study in class 11, 12 in school. There you assign probability to sets and that is okay. So, an experiment results in various outcomes, like this rolling die results in up to 1 to 6. Let us say what is the probability of getting an odd outcome. So, if all the possibilities are more equally likely, odds are like 1, 3, 5 and the evens are 2, 4, 6, because they are same number, you said let us say half. Now, this kind of blunt set theoretic probability is very restricted in the scope, because this always basically to study this kind of probability you will have to always get back to the experiment and understand how the sets are coming from that experiment. This experiment always lurks there. You cannot go very far theoretically, you cannot analyze the underlying general how randomness in general works. I mean tossing a coin, rolling die, these are random events, like you do that, potentially one of several things can happen. The properties of these kind of things in general cannot be understood very well if you only study from in a case by case fashion. The introduction to random variable, the notion of random variable, gives us a unified approach to study all such situations. So, random variable essentially it is a numerical functions which is broadly speaking what it does, its values enumerate the outcomes of an experiment, potentially enumerates the outcomes of an experiment. So, for example, if you toss a coin, if you get head you call it let us say 1, if you get tail you call it 0. So, random variable is a numerical enumeration of the outcomes of an experiment. So, for any random variable x and a set A, there exists a probability of that set belonging x belonging to A. So, you are doing a random experiment, you have enumerated the outcomes by numbers, you are asking what is the possibility that the number that you are getting as a result of that experiment belongs to a particular set. It is like asking what is the probability of getting head when you toss a coin. If you enumerate head by 1 and tail by 0, you ask what is the probability of getting 1, what is the probability of getting value 1. This makes us approach the problem in a mathematical fashion. So, as we just orally said, random variable is basically outcomes of all possible values, but it does not have to be just one value, the numerical values, it can also be a vector. The outcome, you may potentially enumerate it by the outcome by a vector. For example, if you are rolling a die, you enumerate it by 1 to 6, just keep the same numbers, and if you toss a coin, you call it head, you call head to be 1, you call tail to be 0. Now, if your experiment is that you are simultaneously tossing a coin and rolling a die, let us say x is the outcome of this simultaneously tossing a coin and rolling a die. So, if your x so I just wanted black, sorry. Suppose x is the just one second, I want it little thicker, yeah, x to be I and j, where I running from 0 to 1 integers, or I equal to 0 and 1 and j equal to 1, 2, 3, 4, 5, 6. So, value of x equal to 1 j, this means this is you get when head plus j, and j in when j is 1 to up to 6, you roll a die, you get one of the values. So, you let us say you enumerate x, the outcome to be 1 comma j if you are getting head and j, and equal to 0 and j if it is tail and plus j. So, if your outcomes are complex like this, it involves multiple, so your experiment is itself is a combination of multiple experiments, then potentially taking vector valued outcome, vector valued enumeration gives you little more freedom. So, that is called, the single valued generally is called random variable, vector valued is called random vector. A sample generally is n random variable having the same distribution p. The distribution means the totality, the behavior of this background population. This background population, outcome of some experiment, by the outcomes need not be discrete like 1, 2, 3, outcome of an experiment can be just, I think I discussed this at some point in one of the class back, one of the previous classes, where your experiment is simply randomly pick up a point between 0 to 1. So, it can be any real number between 0 to 1. So, outcome need not be a continuous thing, it can very well be, it need not be discrete thing, it can very well be a continuous, coming from a continuous spectrum. So, and generally speaking, a sample or measurement, the measurement that you are actually doing to do the prediction is called that sample, that is basically n random variables having the same probability distribution as the population, meaning you have an experiment whose outcomes have certain probability structure, that is this outcome has this probability, this outcome has this probability, and so on. You do the experiment n times and denote that the outcomes by x1, x2, xn, that is called the sample. So, the measurements done based on which you will predict the outcomes of or behavior of all possible potential measurements is called the sample. And for some random variable x, the cumulative distribution function is this one, is defined to be probability. So, fx of a is probability x less than equal to a. This is, it will become clearer, this is actually quite important in the context of probability. And for random vector, cumulative distribution function is a vector valued function, fy a1 a2 an is probability y1 less than equal to a1 dot 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 yn less than equal to an. Now, just like in case of when you are talking about you are taking an height of bunch of students, let us say you have 3 students, one has height 5 feet, another has another. So, suppose you have 2 students, one of them has height 5 feet, another has 6 feet. You can talk about average height. Suppose based on these 2 students, you want the average height of these 2 students based on this information that one has height 5 feet, another has height 6 feet. Your average height is 5.5 feet. That is a classical average. Now, suppose you have a situation where you have 2 students of height 5 feet and 1 student of height, let us say. So, okay, you have 2 students of height, just one second. So, let me just do that, give you the calculation. Suppose you have 2, suppose you are interested in heights of people. Suppose you have 3 people, 2 with height 5.5 feet and 1 with height 4 feet. What will be the average? Well, it will not be 5.5 plus 4 divided by 2. This is not the correct thing. What you will do, 5.5 times 2 plus 4 divided by 3. So, you have to consider not just the heights and take their blind average, you also have to consider the weights, how many people are coming with that height. Now, this is what weighted average is, I am sure you know. So, basically what we are trying to guess, so what is the probability of getting a person, if you take these 3 people, what is the probability that a person amongst these 3 has height 5.5? Well, there are 3 people, 2 has height 5.5 and 1 has height 4. So, the probability here having height 5.5 is actually 2 out of 3. So, 2 over 3, and probability of having height 4 is 1 out of 3. Now, this, observe this 2 over 3, this is the probability here, and this 4 over 3 is the probability here. So, probability essentially gives you a notion of normalized weight. Here, if the weight is 2, for 5.5 feet weight is 2, 1, and for 4 feet weight is 1, the normal weight in general is 2 and 1, but the normalized weight is 2 over the total weight and 1 over the total weight. So, probability is essentially the normalized height. So, this is how for any experiment, any outcome of experiment, if you once you enumerate that using the random variable, one can talk about average value of that random variable. So, if probability, recall weights are probability is normalized height, normalized weight. So, remember if the values are weight, I will fill up this column. So, values are A1 weight is W1, AN WN, these are weight. Now, we define normalized weight as W1 over W, Wn over W, where W is just the sum of the weights. We call Pi, the probability here essentially becomes this normalized weight, and average is nothing but summation Ai Wi over W, which is same as summation Ai Pi. This is exactly what is happening. So, and there is nothing special about average of the random variable itself. You can take the average of rth power, where r is 1, 2, 3 dot dot. So, when if x takes value small x, x power r takes value r x. So, you just take the basically the x power r takes value x power r, you basically take these values and multiply by their normalized weight. So, that gives you the average. So, this is average of x power r. And similarly, one can define variance. Well, these are moments, so these are the averages. Moments are just averages. One can define something called variance. So, moments, rth moment, average value of x power r. So, remember, so or this is, there is this word called mean. So, this is average value or mean value of x power r, and this is variance. So, this is we only define for x only, not for power. This is the spread of values of x. See, recall that if you have a data like this, it is a two-dimensional data, mean is the center and this spread, variance is the spread. So, this is what spread is, and this variance is basically mimicking that. We will get into more when we are discussing about samples and etc., then we will get into the relation between these values. So, it just basically what is going on, I mean, if you, it's probably not clear from this formula, what this is equal to expected value of x minus expected value x whole square. So, you are taking this mean of x first of all, and taking for every x the distance, squared distance from its mean, and taking the average value of that. One can show that these two are equal. So, that is basically what you know about variance for given bunch of points. So, x average of the squared distance from the mean, and there is something called covariance. This is essentially how they are spread together. We will get into covariance later, but covariance basically indicates, higher covariance indicates if x increases, y increases, normalized by the variance, and the converse. So, finally, the moment generating function of x, the random variable x, is basically the average of this function e to the power t x. The importance of this is that the kth derivative of moment generating function actually gives you the kth moment. We really are interested in the sample moments, because we are not only interested in how x behaves, how the powers of x behave, and so how the spread is that, and how the center of the spread of various powers, and this function is really cute, because just once you somehow calculate this, you can calculate all the moments by simply taking derivative and putting it to 0. Now, note that this is a function of t, this is a function of t, because for a fixed t the x takes various values, but e to the power t x depends on t. So, for a fixed t you get this sum, assuming it converges, that gives you for every t a value for this sum. So, for every t you get a value, so that gives you a function of t, that is your mxt. Now, this function of t, this mxt, if you differentiate it with respect to t k times, you will get an expression, plug t equal to 0, you get kth moment. So, just some example, some probability distribution. So, one is discrete uniform. So, this is basically captures the behavior of an experiment where outcomes are 1 up to n, just like for example, if n equal to 6, just rolling a die, the results are 1 up to n, and suppose all outcomes have equal likelihood of coming out, that is 1 to n, everything has chance 1 over n. That is called discrete uniform distribution. One can check that these are the probabilities. This is just expected value, you can calculate it by summation x takes value 1 to n, each of them has probability 1 over n. So, I running from 1 to n, this is 1 over n times summation I running from 1 to n, and this is the arithmetic progression, this is n times n plus 1 over 2. So, this is n plus 1 over 2. And the variance also can be calculated in the same way. It is a summation I square 1 over n, I running from 1 to n. There is a formula for that also, summation I square, there is a formula for that, that gives you this expression. And similarly, one can calculate the moment generating function for this distribution. So, let us move on to another interesting. So, this is, by the way, I added the calculation here also. I forgot that I added the calculation. This is the summation of the square. So, whenever you are dividing by this, you just basically get this, and this this is expected value of x square basically. So, the variance x will be expected value of x square minus expected value x whole square, and that will give you this thing. So, you can check this is simple difference between two polynomials, and there is nothing spectacular. It of course depends on n, because you are doing it, your distribution itself is dependent on n 1 up to n. Second is binomial distribution, binomial NP distribution. So, here what do? You have a coin with head probability p, you toss it n times, count the number of heads. Now, if you denote that by x, the number of heads, there can be 0, 1, 2 up to n many heads. What is the probability of getting 0 heads? Well, all the tosses will have tail, 1 minus p power n. What is the probability of getting 2 heads? So, suppose you have 10 tosses, probability, so probability of, let us say, suppose this is head is 1/3, probability of 2 head. So, you have 10 positions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The thing is, you can get 2 heads from any of the positions. It can be from 3, 7, it can be from 1, 5, it can be from 2, 10, anywhere. So, how do you choose those positions? Well, in 10 choose 2. Now, in those positions you will get, so in those positions you are getting head. So, the probability of getting head there in those 2 positions, each of the position is 1/3, and there are 2 such positions, 1/3 square, and in the remaining positions you get tail. If head probability is 1/3, tail probability will be 1 minus 1/3. So, this, and there are 8 such positions. So, the probability will be 10 choose 2, 1/3 square times 2/3 power 8. But nothing really special about 2 and 10. If you are taking n positions and head probability p, out of that if you get, what is the probability of getting x many heads? You choose x positions out of n, n choose, or ncx rather, I mean this, n choose x, it is same as ncx. You will see those both the notations in literature, the c for choose, they are same notation. So, you take, once you have fixed x positions, you take, in all of them you will get head, and the other n minus x you will get tail. So, you are tossing 2 coins, what is the possibility of getting head first and tail later? Head probability p, tail probability 1 minus p, p times 1 minus p. This is exactly what you are doing. In those x positions you are getting p, the remaining 1 minus p. So, p to the power x times 1 minus p to the power n minus x. By the way, probability of everything should be 1. probability of everything should be 1, and you can check this is 1, probability of everything is 1, because after all we take probability to be between 0 to 1. So, probability of everything is 1. Here one can check that probability of x going to 0 to n ncx p to the power x 1 minus p to the power n minus x, one can check this is nothing but p plus 1 minus p power n by binomial theorem, which is binomial theorem which gives you 1, because this is just 1 power n. The name binomial distribution comes from there. One can check the expected value, the mean there. So, first moment is also called expected value. So, this is also called average of x, expectation of x, expected value of x. All these are interchangeable, these terms are interchangeably used. Mean of x, they basically indicate average, and one can check variance is np times 1 minus p, and moment generating function is this. Now, we discussed that one can the experiment need not be you just select one amongst finitely many or discretely many values. It can also very well be coming from a continuous spectrum. You can choose randomly a number from 0 to 1. It can be any real number between 0 to 1, which is a sort of a continuous spectrum. Now, if you think about this, if you choose, what is the chance of, if you choose randomly a point between 0 to 1, what is the chance of picking up a point which is equal to half? People will say 0. Same thing for if you pick up a point which from 0 to 1, what is the probability of this being 0.01? Just 1 point out of infinity, people will say 0. However, if I ask you what is the probability that you pick up a point between 0 to 1 and it falls between 0 to half, instinctively people will say half. What is going on? If you have infinite, so the point is that if you have infinitely many points, you are picking up a point, it has to come from somewhere. So, pick a point at random from 0 1, call it x. Probability x equal to a equal to 0 for all a in this means for all. This is a standard notation in mathematics. So, for all x a in 0 to 1, but probability x equal to x belonging to an interval c d equal to d minus c over d minus c, where c d belongs to 0 1 and d greater than c. What is the mystery? No mystery here. Basically, 0 times infinity, this is undefined. So, just because you are getting 0 for every point, that does not mean you kind of add infinitely many of them and you will get 0. So, this can potentially be anything, and this example tells you it is possible to assign probability to non-zero probabilities to sets where probability of each point is 0, and this is what the continuous or absolutely continuous, the more rigorous term is absolutely continuous. This is the situation where of absolutely continuous random variables. So, here absolutely continuous random variable x is absolutely continuous random variable if for any set, frankly I am avoiding some mathematical nitty-gritties here. You cannot really assign it to any set of real number. There are basically there is something called measurable set. You can only assign probability to measurable sets. I am just allowing some lack of rigor at this point, but let us say for nice sets you can assign probability inside that, probability of x belonging to that set via integral of a function. So, this function is called the probability density function or PDF of x. So, you know that probability of x belonging to minus infinity to infinity is 1, and for any interval you just take the integral of fx from a to b, where a is the left hand point and b is the right hand point. And for any point, most importantly, any fixed point, probability of x belonging to that, x being that fixed point is 0, just like we discussed in the uniform example. So, for continuous, the same way as discrete, one can define expected values. The intuition behind it will be clear more you get used to it. Just like for discrete, you take the values of x, multiply by probability, which is normalized weight, and take the sum. Here you are multiplying x by fx dx. So, for basically for a small interval dx, because fx remains more or less constant there, the probability there is fx times dx. It follows from the area interpretation of integral. So, it is essentially the probability of x being in the small neighborhood of around x is fx dx, and this integral is essentially sum of x times fx dx, and x remains sort of constant in that neighborhood. So, that gives you the value coming from that neighborhood, and you are taking the sum of that. That is the intuition behind expected value. Similarly, you can define expected value of x power r, cumulative distribution function we defined before as probability x less than equal to a. We defined moment generating function, and in case of continuous also moment generating function, you can differentiate it k times with respect to t, and you will get the kth moment. I just, before I move on to something else, just quickly want to give you some continuous probability distribution. This is the uniform probability distribution we discussed. Nothing specific about 0 1, you can even take it a to b, and the expected value the continuous for the, if your density function will be 1 over b minus a, expected value will be the midpoint. You can calculate variance and moment generating function in the same fashion. Here is a calculation for that. Expected value is just x times the density, and you are taking the integral of x gives you x square divided by x square divided by 2. So, that gives you b square minus a square, and you are dividing by 2 times b minus a, that will give you a plus b divided by 2. Similarly, you can calculate x squared, expected value of x squared, and you can find the variance. This is another distribution. This is extremely important. This is this bell shaped distribution. This is called normal distribution. For various mu and sigma, you can get various normal distribution. This will be mu, and the sigma, bigger sigma means spread, more spread it is. So, this is less, this is sigma 1, and this is for sigma 2 bigger than sigma 1. So, more the sigma is, more spread out the distribution is, and it is centered around this object called mu. So, for normal distribution, it is known that expected value is mu, variance is sigma square. This is the moment generating function. Normal distribution is extremely important and ubiquitous in probability statistics. In the reason for that is will become more clear. Essentially, what happens is that if you do same experiment repeatedly and take their average, you do take the more, you do it more number of times, distribution whatever you start with, this distribution of this average tends to become normal distribution for some mu, some sigma in certain way. So, some properties of expected value, if you have two random variables x and y, the expected value follows linearity. Expected value of Ax plus By is A times expected value x plus B times expected value y. If you have a constant random variable, but that is it takes only one value, of course that is the expected value. Average of some, if you have bunch of numbers all basically are same. If you take 10 5s and take their average, you will get 5 only. If you take the average of if you take the average of two random variables, the average of their sum. So if you have one, so if you have 1 2 3 4 5 and you have say 100, so this is your x, this is x1 x2 x3 x4 x5, and you have 100 99 98 97 96, and these are y1 y2 y5. Average of xi plus yj, this set when you take I both I and j between 1 to 5 is equal to average of x plus average of y. This is what essentially is captured here. And finally, the more general part, like you multiply x by a scalar, you take the average is just the scalar times the same average. You take bunch of random variables, average of the sum is the sum of the averages. These properties of expected value are extremely important. We are just, frankly, all these can be proved from definition, both for discrete case and absolutely continuous case, from properties of sum and integrals. We are not getting into the rigorous proof of these things, but I am just mentioning because these will be quite frequently required in this course. Similarly, variance has this interesting property that you multiply a number by a scalar, the variance gets multiplied by square of that scalar. If you scale a number by, you shift a random variable by a constant, shifting like the spread of this area, and if you shift the same area by something, shifting does not change variance, it is the same spread, and variance of a number constant is 0 because constant thing has 0 shift. And finally, when you have a variance of bunch of things, it becomes sum of variance of a sum becomes sum of the variances plus sum of the covariances. So we stop here for today's class. In next class, we will continue with this statistical framework. Thank you.